Hey y'all, this is the third video wrapping up our Chapter 12, Gases. So we really only have a few points to talk about for this last section, and some of it's actually just kind of a summary. These last few parts about gases, kind of summarizing all the mathematical relationships we've developed and sort of grouped together all the main points about gas behavior into what we call kinetic molecular theory. Okay. All of our equations that we use describe sort of like how gases behave and how they operate, and we can predict the changes in the different variables. But it really doesn't explain why they do what they do. So here we kind of have a list of facts and observations about gases that we make. Some of them are kind of just general assumptions that we make that apply to how gases behave. So that's what our kinetic molecular theory is. It's really just a series of points. So let's start off. Our main points here. Okay, first one, pretty obvious. We've discussed already. Gases consist of large numbers of molecules in constant motion. So constant random motion, gas molecules are always moving, unless of course you are at absolute zero, the theoretical temperature where the kinetic energy of the gas molecules is zero, so then they stop moving. But other than that, gas molecules are always in constant motion. Constant random motion. Okay. Second point, kind of assumption that we make. Gas molecules no, I don't like that. Sorry, I had a small error. Don't know exactly what happened. I started erasing a bunch of things. Okay. Sorry, I want to restate that differently. Okay, let me fix my in there really quick. Okay. The volume of gas molecules is negligible. All right. Relative to the volume they take up. Let's see, relative to the volume, I'll say they are contained in. All it basically says is when we consider the volume of a gas, we don't consider the size of the actual molecules. They're really, really small. So even when you have trillions of them all added up together, sure, that does take up a little bit of space. But in order for most of the calculations, we say the volume of the gas molecules don't take up any space. Okay, so when you have like a 5-liter container, you don't say, well, okay, yeah, that's a 5-liter container, but there's some gas molecules in there and they take up some space. So really it's a little bit less than 5 liters. You don't make that. You just say, hey, they take up 5 liters and the volume of the gas molecules doesn't affect anything. Okay, next on our list, attractive forces and repulsive forces. Repulsive forces are negligible. Between molecules. So again, all we're saying here is that, hey, as the molecules collide with each other and they exist in space with each other, we ignore all the attractive forces. So hey, if you have like sort of polar gas molecules, right, that might be attracted to another polar molecule, well, yeah, sure, that's probably going to happen, but we ignore it in terms of all the attractive force. Okay. Next point. Fourth point. Don't worry, there's only 5 main points, but we got a couple of extra ones after this. Okay. The energy transferred between molecules when they collide so they're bouncing around, colliding with each other and their container, does not change. And I'll put in parentheses, as long as temp is constant. So as long as the average kinetic energy, which is temperature, as long as the average kinetic energy is the same, well, then the energy transferred between molecules as they bounce around has no effect. So, you know, when a molecule collides with a container, sure, it's applying a force, and in, you know, just like in when you guys discuss in physics, you know, when something collides, it loses a little bit of energy and slows down and continues to stop moving. With gases, we say no. When they undergo their collisions, they keep moving at the same space. So it's really perfect. It's like a perfect elastic collision. Okay, no energy transferred whatsoever. All right. Again, as long as the temperature remains about constant, that's the average kinetic energy. So yeah, on a molecule-to-molecule basis, energy is being transferred. But if the average is the same, well, then we just ignore that. Okay, last point. Speaking of average kinetic energy, so the average kinetic energy of our gas is always proportional to Kelvin temp. Okay, basically our absolute temperature, no negative values. Okay, so kind of another way to say this is, if you have gases at same temperature, what that means is they have the same average kinetic energy. Average kinetic energy. Okay. So those are our main 5 points to kinetic molecular theory. So these 5 points represent great talking points on how to describe gases at the molecular level, using these key terms like collisions, average kinetic energy, transfer of energy, things like that. You can really help describe how gases behave at the molecular level. In free response questions, these are the kind of terms you want to use to describe gases and their behavior. Okay, moving on. We have a couple of topics, okay, here I want to show you guys this graph here now. So here we're looking at molecular speed, the speed at which molecules are moving at. Okay. Now, when you have a gas sample at the same temperature, they have the same average kinetic energy, right? But that's an average. Individual molecules, though, are all moving at their own variable speeds. Okay. So when we look at a graph like this, we see here we have like a fraction of molecules, right? So how many of those molecules are moving at a high speed? Right? So if we look at something like hydrogen, H2, more hydrogen molecules are moving at higher speeds. Right? It looks like hydrogen peaks somewhere around here. This is probably around like 1,700 meters per second. Okay? And we definitely have some moving at the highest speed of all these gases, over 3,000 meters per second. We see helium The second fastest peaks somewhere around here. Maybe that's arguably 1,200, maybe 1,100 meters per second at its greatest number of molecules moving, but then peaks somewhere just above 2,000, not quite matching hydrogen. And we keep seeing a drop-off. Here are water vapor molecules, nitrogen molecules, and oxygen molecules moving the slowest, right, of all of them. The average number of the fraction of molecules for oxygen moving are the slowest speed of all these. Okay, so you might be asking, well, what's the difference? Well, the key here is mass, molar mass. Okay, we see here hydrogen having the smallest molar mass, has a molar mass of 2 grams per mole. Helium's up to 4, water's up to 18, nitrogen's up to 28, and oxygen's up to 32. So it's kind of a nice relationship, right? The heavier molecules move slower. Okay? Heavier molecules move slower. And therefore, they have a lower molecular speed. I don't really think I need to write that lighter molecules then would have a greater speed and would be able to move faster. So all this talk of moving brings up a couple of different terminologies. We have terms that are called effusion, and we'll look at diffusion here in a second. So effusion basically talks about the movement of gas molecules through a small pinhole and they're going to move to an area of low pressure. So if you can imagine inside of a container, try to draw a simple one here. Let's change our color really quick. Probably didn't need to draw it that big, but that's okay. Alright, so here's our container. And let's say there's kind of a divider inside the container, right? And in that divider is a small hole. So now you have your gas molecules all bouncing around in here, right? Lots of them. These are terrible looking gas molecules. Oh, anyway. Okay, so they're all bouncing around, bouncing off of each other, zipping around. I'm not going to draw arrows all over the place. It's going to get really messy. Now, obviously there's lots of gas molecules in this upper half, so the pressure up there is much greater than the lower half. Well, eventually, some of these gas molecules are going to start to move down here. Slowly but surely, we'll start to collect them. That's basically the definition of effusion, right? So now this question comes up. We're asking, like, which gas would effuse faster, right? Lighter gases are going to be moving faster, and therefore they are going to be moving through that pinhole at a higher rate, right? So let's say you have a mixture of, I don't know, let's say up here you have, let's just go with oxygen and hydrogen, okay? And the question might be, which of those two gases are going to move through and effuse faster than the other? So hydrogen, being your lighter gas, will collect faster down here. So sure, some oxygen molecules will make their way through, but hydrogens will make their way through at a much higher rate. Okay, so maybe I drew 3 molecules, 3 little gas molecules down here, one here, one here, and one here. Let's say, for argument's sake, 2 of them are hydrogen and 1's oxygen. All right, or maybe they're all 3 hydrogen and oxygen hasn't made its way down yet. But based upon its mass, hydrogen will be moving faster, therefore will have a greater probability of making its way through that pinhole and collecting into the lower half of the container. That's the whole idea behind diffusion. Now let's look at diffusion. So diffusion, I know they sound the same, but they do have different definitions. Diffusion is all about mixing gases. This is all about them moving around each other. So an awesome example of this. Okay, well, first of all, let's talk about this. So you have gas molecules in constant motion, right? So they're going to have to move through each other. So if you mix 2 gases together, they're going to spread out and expand and take up the space, right? They have to fill up the volume of whatever they're in. And as they do that, they're going to move through each other. They're going to bounce into each other, those 2 gases. That whole idea is called diffusion. So a good example of that is, let's say, perfume, P-E-R, right? Okay. Perfume in air. Okay. So air obviously is a gas mixture, and then somebody sprays perfume. If you're sitting in a room, a crowded room, and one person in one side of the room, one corner of the room, sprays perfume, the people next to that person will smell that perfume first. But it takes time for that perfume, that gas, to diffuse through the air and make its way all the way to the people, let's say, at the opposite corner of the room. It'll take maybe a minute or 2 for them to actually smell it. Maybe they won't smell it at all because the gas diffuses and expands beyond the point of, well, you as a human being able to smell it. But the concentration of the perfume immediately is very high as it spreads out. That whole idea of diffusion, right? Gases moving within each other, other gases, just spreading out. That's what diffusion is. Okay. So now to kind of summarize some of these relationships about effusion and diffusion, we have kind of a simple equation that does come in handy. More than just using the equation, we use it to figure out these relationships. The rate of effusion of a gas, let's say gas 1, I'm going to run out of room here. Oh well. Rate of effusion of gas 1 over the rate of effusion for gas 2 is going to be equal to the square root of the molar mass of, run out of room. No, this is going to be of gas 2 divided by the molar mass of gas 1. So really right here, this equation represents the idea that the lighter gas will effuse through a pinhole faster than a heavier gas, and also says that a lighter gas will diffuse through a room faster than a heavier gas. One really neat demonstration that we can that I do every now and then, and I'll show this to you guys later in the year. Actually, no, I'll do it in class. Anyway, but if you're watching this, maybe you missed class, so you can look up a video of this demonstration. It's really a neat one. We can take a jar of concentrated hydrochloric acid. Okay. Hydrochloric acid is very fumy, right? That's hydrogen chloride moving up into the air. We could also take another jug of concentrated ammonia. Again, very fumy, very strong smell. Both of these have very strong smells. You open up both lids on these 2 bottles, and you can just see the fumes go up into the air, and they can actually move. What's really neat is that when these 2 gases mix, one of the things they'll form is ammonium chloride, which is actually a white solid. Okay, but it's kind of neat where they actually collide. When you look at the two fumes, you can see a white cloud show up as the hydrogen chloride molecules move up into the air. Guess what? The ammonia molecules will move up through the air, but they'll move a lot faster. And they'll actually collide closer to the hydrogen chloride bottle. Right here. Okay? And, oops. Right here is where we see ammonium chloride form. Okay? It doesn't form right in the middle. It doesn't form here in the middle. If it formed in the middle, that meant that, hey, they actually diffuse through the air at the same rate. But their masses are very different. Hydrogen chloride is much heavier than the ammonia gas. This only has a molar mass of 17, whereas this is pushing 37 grams per mole. Okay, so this gas moves through the air much faster than the hydrogen chloride. And it's really neat. You see this little white cloud sort of develop. That's the ammonium chloride. So again, just a little proof, small, simple demonstration, this idea that gases can diffuse through other gases, and that's dependent upon their molar masses, how fast they move. Okay, final thing we have to look at is this idea of real gases, right? We have our ideal gas equation, right? We have ideal gases. But ideal gases are for gases at relatively low pressures, okay, and where the temperature isn't too far extreme from, say, room temperature, doesn't get too high or too low. So we're talking about non-ideal behavior. We're looking at real gases. Okay, we really just need to worry about the conditions. All right, so an ideal gas becomes non-ideal if we are at high pressure. Or if we're at really, really low temperatures. Okay, so it's kind of interesting if we can look at each one of these variables individually. If we have a gas at a low enough temperature, right? Low enough temperature, gas molecules are slowing way, way down. Okay, average kinetic energy drops. The size of the molecule becomes important. So if you look back at our kinetic molecular theory, we said, hey, the volume of a gas doesn't depend on the size of the gas itself. We don't really worry about it. Well, when we start getting to low enough temperatures, the gas molecules start to collect, and their size actually does become important. It does take up a significant amount of the volume of the gas. So it kind of ruins that kinetic molecular theory point. And now we have to worry about this point. Now, when it comes to pressure, similar thing happens. Okay, at high pressures we start forcing all of our gas molecules together. Okay. I shouldn't say are. I'm going to change that word are to can be. So molecules can be attracted to each other. So those forces we ignored as part of our kinetic molecular theory, guess what? Now we have to worry about them. Molecules can be attracted to each other. Or they could be attracted to their container. Okay, so in other words, forces are important. The forces between the molecules do become a significant factor. And that's about it. That's all we have to worry about. Those are the two conditions that would need to be met. One of them, either one. They don't both have to be there, but if you have a gas under extreme high pressures, we would say it's not behaving ideally. And so some of the equations we might use on it wouldn't really work out perfectly. Now again, you're not really going to be doing any math with real gases. You just have to worry about the conditions in which they exist. Okay, so it's really just conceptual type questions dealing with these 2 points. All the math is always done assuming that gases are ideal. Okay, you're not going to be asked to worry about calculating for real gases. But just know the conditions in which real gases apply. All right, that does it for our Chapter 12 gases. Make sure you guys are practicing working on your problem sets and going over all your homeworks, checking your answers. Let me know if you guys have any questions.
Made with Doodlecast Pro.